All right, 16.2, we are going to, my notes are off a little bit here, sorry about that. Talk about the wave nature of light. So and 16.1, we got a little introduction to what light is. Let's talk about the wave nature of light. So, diffraction is the bending around a barrier. Remember, there are three ways in which any wave can move: reflection, refraction, diffraction. And diffraction is what we're going to focus on. And when we talk about the wave nature of light, we're going to focus on color. Now, we know the spectrum is Roy G. Biv. Violet is the shortest wavelength that has the most energy. Red is the longest wavelength, has the least amount of energy. When we talk about light, how do we get color? We separate white light. White light is composed of all colors. Now, you have to right now take your art background in pigments and completely throw it out the window, because lights and pigments are two different things. Lights and pigments are two different things. If I combined all the colors of pigments, you would get black. But see, when you take light, I'm going to take all the colors of light. I'm going to get white light. Now, the primary colors of light. There are primary colors of light. Three primary colors of light are red, blue, and green. And that is actually significant, red, blue, and green, for multiple reasons. First off, biologically speaking, our eye is naturally keen to seeing those three colors of light, red, green, and blue. Those are how your TVs are pixelated in those colors, red, green, and blue. Now remember, that's different than pigments. So you take red, green, and blue. Those are the primary colors. Combined, they form white light. If you take two primary colors and combine them together, you're going to get three more colors, just like on a pigment. And when you combine three primary colors together, two of the three together, you're going to get the secondary colors. And the secondary colors are yellow, cyan, and magenta. Complementary colors are two colors of light that combine to make white light. And our complementary colors, if you take yellow or blue light, you'll make white light. Cyan and red will make white light. And magenta and green will make white light. So primary colors, secondary colors, and complementary colors of light. So to kind of give you an idea of what that looks like, on the left side we have our pigments. Combine all our pigments together, as I said, you make black. Our three primary colors for pigments are green, orange, and magenta. Throw that out the window. Let's talk about light. Our three primary colors for light, red, blue, and green. Our three secondary colors, magenta, yellow, and cyan. Combine them together and you make white. So just a little heads up there with each one. So kind of distinguishing the difference. Now, when we talk about dyes, subtraction, color by subtraction of light. When we talk about dyes, molecules that absorb certain wavelengths of light and reflect or transmit others. We see red because white light hits it and reflects red. So what that means is it's absorbing blue and green and only reflecting or transmitting back red. So that is kind of how dyes work with light. Now when we talk about dyes, we have primary pigments, absorbs only one color and reflects two back. So if we look here, if I have a primary pigment, it is only going to absorb one and reflect two back. So for example, if I have a red primary pigment, it's going to absorb red. So it's going to absorb red, and what it's going to kick back is green and blue. So what will that pigment actually show? Cyan. Likewise, if we have a secondary pigment, so another example that we talked about. If we have a secondary pigment, it's going to absorb two primary colors. So red absorbs green and blue. So again, we go back here and we look. Red, a secondary pigment. Oh, geez. Just hit my keyboard. Didn't want to do that. Red is going to absorb going to absorb blue. It's going to absorb green. What's it going to kick back? Just red. So that's kind of how red works. That's kind of how our pigments work. They're absorbing one or two types of light and reflecting back one or two types of light. So that is how pigments work. Primary pigments are secondary colors. So what we just talked about here on my primary example again. Yellow is going to absorb blue. Let's not even go yellow, because let's say this again. All right, I have a yellow pigment. What it's going to do is it's going to absorb blue. So blue is gone, and it's going to reflect red, and it's going to reflect green. Well, when red and green mix, they make yellow. So primary pigments are going to make secondary colors because they're only blocking out one of the primary colors. Secondary, because it is secondary, is blocking out two primary colors, and then you're only going to get the one primary color back. If there are questions on that, we can talk about that in class. Switching gears here, and we talk about the polarization of light. Light is an electromagnetic wave. The visible light that we have is an electromagnetic wave. So what we have is we have an oscillation. So we really have two waves in one. In the red, we have the electric part of the wave going up and down, parallel or longitudinal, perpendicular to the motion. So that would be transverse. Likewise, the magnetic part of the wave is going parallel, which is going longitudinally. What I can do is, what's kind of neat, and we'll show this in class tomorrow, is I can polarize the light. I can filter out one of those two. I can filter out the up and down wave, or I can filter out the side to side wave through kind of what's a polar lens, which kind of has slots like this. And what that allows is that'll allow the waves to go up and down through this lens, but not side to side as the grills here, the blue, or these grills that I'm marking in green again, will block any side to side motion. But if I'm going up and down, I can go through it. But if I'm going side to side, boom, I'm going to hit that grill and it's going to filter out some of that light. When you see this work, it's a really cool concept. But polarization is you're blocking one of the two types of light out, the electro part or the magnetic part. And what it's going to do is polarization by reflection helps cut down, you can darken light. Sunglasses work this way. Windows, tint in Windows has some type of polarizing filter on it. And like I said again, we'll do an example of filtering by polarization in class tomorrow. Speed of light. Since we're talking more about wave properties, we already know that light travels at 3.0 times 10 to the 8th. That's good. Different colors of light have different frequencies and different wavelengths, but they all travel at the same speed. We talked about Doppler effect with sound. We did the NASCAR effect with sound, where it's how you perceive the frequency or the pitch. If something's moving towards you, the wavelengths bunch closer together. If it's moving away from you, they get farther apart. The same thing happens with light. If an object with light is moving towards you, the wavelengths are going to be closer together. And if they are moving farther apart, it's going to be farther, or if it's moving away from you, it's going to be farther apart. And this is called what astronomers called red shift, blue shift. And this is how we can tell whether or not a planet or another astronomical body is moving away from us or towards us, is by the color of light that it's giving off. It's slightly tinged red or blue. Now we go back to the very first slide in which we were talking about here. Violet is the shortest wavelength. So if something is moving towards you, it has blue shift. If something is moving away from you, since red is a longer wavelength, it's going to appear tinged in red. So that is our red shift, blue shift. A couple things here with interference. Real quick, some more vocab. Very heavy on the vocab intensive part. Interference. Just go through some vocab here real quick. Incoherent light, unsynchronized wavefronts, coherent light, lights from two or more sources that added together make superposition or good constructive interference to produce smooth wavefronts. Monochromatic light, light from only one wavelength. Then we have something called thin film interference, spectrums of colors as a result of constructive and destructive interference of light waves due to reflection in a thin film. So this is light being reflected in a thin film. You guys ever see oil in the water and how it kind of has like a rainbowish tinge to it? Or you blow a bubble in the sunlight and you see kind of that rainbowish tinge to it where you get a variety of all colors? That is thin film interference. An example of how light can be slightly interfered through a thin film, such as an oil slick on the ocean or in a lake, or just a bubble on the surface of the air or on a table or anything like that. Diffraction. Don't worry about diffraction. We'll talk about that in class. I'll do an example of that we can explain in class. It'll make more sense. So I know it's a lot of information in one shot for light. If you have questions, we will talk about each kind of one of these vocab words with light, and you will have a packet in class to do tomorrow.